So as we mentioned in the previous segment on fatigue design, in real life, fatigue takes place under very complicated conditions. The shape of the material is different from the simple rotating beam test specimen. The loading is not bending type loading, but could be torsion or shear or any kind of combination loading. The temperature is different because we get the material to be tested at room temperature usually. The size of the component is different. The surface conditions are different, and so forth. So to account for all of these, Marin, Marin, that's the name, has introduced a number of factors that account for the environment and for the exact shape and for the exact geometry and conditions of the specimen that we are interested in or the component we're interested in. So I will outline those here, and these are empirical factors. We can list them and try to understand how to compute them. Then we'll take some example. And then the other topic that I'd like to talk about today is called fatigue notch sensitivity. And as we will move with our designs of rotating shafts under transverse loading, we'll find that the shaft doesn't have a uniform cross section, but it actually is stepped by design so that we can attach other devices such as gears or pulleys. And every time we step the shaft from its original size to either a larger or smaller size, then we have to make it a fillet so that we don't have excessive stress concentrations. Nevertheless, we have a region of stress concentration. So under normal conditions, we can go to the design handbook and find the stress concentration factor given the fillet radius and the small diameter and large diameter radius, and find the stress concentration factor. However, under fatigue conditions, this stress concentration factor, which is obtained for static loading, is changed, is different. And the reason is you get some localized plastic deformation, and the localized plastic deformation helps it's like a massaging, so it helps to spread the plasticity and reduce the effective level of the stress concentration factor. If there's no plasticity, then the fatigue stress concentration factor should be pretty close to the static stress concentration factor. And in this case, we say that the component is very sensitive, has a very high notch sensitivity factor. However, if plasticity plays a big role and the material is very ductile, then we find that the fatigue stress concentration factor could be quite a bit significantly smaller than the static stress concentration factor. So these are the two things I'm going to cover today: the endurance limit modification factors due to Marin, and then the notch sensitivity. So let's look first at the Marin endurance limit modification factors. So the way that he expressed those is that we have the endurance limit, which is in practice, is basically a combination of seven factors basically: Ka times Kb times Kc times Kd times Ke times Kf. All of this is multiplied by the rotating beam endurance limit. So Se prime is for the rotating beam, which we get from tensile experiments. So when we have now the try to reduce the level here. When we have these factors, we're going to write them down as their names imply. The case of A is the surface factor, and the case of B is the size factor, and the case of C is the load factor, and the case of D is the temperature factor, and the case of E is the reliability factor, and the case of F is a miscellaneous factor for other effects. So the way that these empirical factors are done is that if we look at the surface factor case of A, it is expressed as a constant times the ultimate strength to another raised to another constant. And the values of A and B will be obtained from tables, as I'll show you in a minute, depending on the surface finish. The size factor is also obtained, case of B, as the diameter divided by 0.3, this is an inch, to the minus 0.107, and that is for diameters that are in the range of 0.1 inch to 2 inches. And then it has a different form for larger diameters, as I'll show you. The load factor is K sub C and is equal to 1 if we have bending, because the tests, the rotating beam test is done under bending conditions. So K sub C is equal to 1 for bending, but if we have axial loading, it drops to 0.85, and if we have torsional loading, it drops to 0.59, indicating that shear is more deleterious to the material. The temperature factor is K sub D, is the ratio of the ultimate strength at room temperature. This is at any given temperature, so a given temperature, divided by the ultimate strength at room temperature. So if the ultimate strength decreases at high temperature, that ratio becomes less than 1. The reliability factor, K sub E, is half for if we desire reliability of 0.5 let's say reliability of 0.5 or so, sorry, if we have a reliability of 1, like 100% reliability, then we can use K sub E equals 0.5. If we want to get along with lower reliability, then this factor becomes smaller. For example, it is equal to 0.897 for reliability level of 90%. And then the miscellaneous factor accounts for residual stresses, accounts for corrosion, and so on. Many different effects, and that is determined essentially by the exact testing conditions. So this is an overview of the factors that can modify the native endurance limit that is measured by the rotating beam specimens, and then we can apply it in practice. So this is kind of a general overview, and now I'm going to quickly show you from the book how to compute these factors when we have a design problem. So here we have the formulation is given as the 7 factors multiplied by SE prime, and you get the description here. And Then for each one, we'll just go one by one. This is the surface factor, and that's computed if we know A and B. And the factor A, if we have it in megapascal, the strength in megapascal. So if we have machine or cold drawn, is 4.5, and B is minus 0.265. So these are tables that we use in design. For example, if we want to have a steel that has the ultimate strength of 520 and it has a machine surface, so we want to estimate the surface factor. From the table, it's machined, so it's 4.5 and minus 0.2, and therefore you have 4.51 minus 0.265. You substitute here, you get that the surface factor is essentially 0.86. Now, if we look at the size factor, as we mentioned, it is the ratio of the diameter by 0.3 inches raised to that power, 0.107. For larger sizes, you get it 0.91 times d to the minus 0.157, and this is all in inch in here. If you have millimeters, then you use these factors. Next is the size factor for cross sections that are not round and rotating. So what we do is that we estimate the volume of the material stressed at 95% of the maximum stress, and then we equate it to the corresponding cross section, assuming that we have a round cross section. So if you have a rotating round cross section, 95% of the area is used. So you get the area at 95% sigma is 0.0766 times the diameter square. And for non-rotating, that's what we found here. And therefore, when we equate it to solve for the equivalent diameter, then we have an equivalent diameter as 0.37 d for a round cross section. For a rectangular cross section, then we can find the area, which for 95% is sigma, and then we also equated to the 95% area for the round, and we get an equivalent diameter. So these kinds of results are summarized in table 6.3, where for every cross section that we can find here in design, we get the A 0.95 sigma and the equivalent diameter for each case, as you can see here. So let's take an example here. In this example, we have a steel shaft that's loaded in bending, and it is 32 millimeter in diameter, and it has a filleted shoulder, 38 millimeter in diameter. So the shaft material has a mean ultimate strength of 690 megapascal. We want to estimate the Marin size factor case of B, if it is used in the rotating mode and the non-rotating mode. If we use the rotating mode, then we would find k sub b directly as because it's in millimeters, so we use d over 7.62, and it's the same coefficient here. Then we'll get k sub b equals to 0.858. In the case that we have a non-rotating mode, then we have to use the equivalent diameter and use the same formula, and it gives us 0.954. So after that, we have a load factor, and the load factor, as we mentioned, is 1 for bending, 0.85 for axial, 0.59 for torsion. Next is the temperature factor, and the temperature factor is expressed as the ratio of the strength at the given temperature divided by the strength at room temperature. Room temperature is 20 degrees Celsius or 70 Fahrenheit. Then that factor is 1. Then as the temperature increases, then you get the factor to increase, and then finally it decreases very high temperature. So it increases very slightly, the strength increases a little bit at intermediate temperature, and then it decreases for higher temperatures. So that temperature factor here, we can obtain it from the table directly, or if we have, say, a MATLAB program, or we want to do hand calculations, we could use an analytical form for this factor for steels, and this factor is given by K sub D, and the temperature is in fact in degrees Fahrenheit, so it's a polynomial in the temperature in degrees Fahrenheit. So we have an example. We have 1035 steel, tensile strength is 70 MPa or KSI, and the temperature is 450. So we want to have the room temperature endurance limit is, if we want to estimate the Marin temperature modification factor at 450, if the room temperature endurance limit is 39, and then we want to also determine the tensile strength at any temperature if it is known. So from the solution, we can use directly the polynomial and find the factor to be 1.0007. So it's nearly 1, and therefore the temperature doesn't have much of a change or an effect on the endurance limit. If we interpolate from the table, which is a different way of solving the same problem, we get 1007, and thus we get the ultimate strength at 450, 1007 times 70. So it's the same, very, very close, and you get 70.5 KSI. So the endurance limit at 450 is half of that from the correlation, and therefore we can estimate it to be 35.2 KSI. Here's the reliability factor, and the correlation that we use, that SE prime is equal to 0.5 S ultimate, represents 50% reliability, which is kind of midway if we look at the data here and put a line through the data. So the line through the data is midway, assuming that we have a distribution function of failures around that, or values around that, then we would take the line as the 50% reliability line. For different levels of reliability, this is computed for us, and for each level of reliability at 90% reliability, then the reliability factor is 0.897. As we mentioned, 50% reliability, the factor is 1 by definition. This is kind of the median by definition. As you require more reliability, then the factor drops down, as you can see, to 0.62. Now the miscellaneous effects factor is very difficult to obtain from correlations, and it depends on the actual test conditions, and those are obtained from company data or from field tests to make sure that we can account for those. So the next topic is the notch sensitivity factor. And the notch sensitivity factor is, as I mentioned, when we have a shoulder in shaft design, we have a static stress concentration factor. As we move from static to fatigue, plasticity can play a role, and in fact redistributes the stress. So we define here a notch sensitivity, fatigue notch sensitivity factor. I'll show you the definition. And once we define it, we have graphs, design graphs based on experimental data and calculations of plasticity. And we use these design graphs for finding the notch sensitivity factor, and hence modifying the stress concentration factor. So the way that it works is that we define the notch sensitivity factor Q to be ranging from 0 to 1. 1 is fully sensitive and 0 is not sensitive, as the ratio of the fatigue stress concentration factor, K sub F, is what we want, at minus 1 divided by K sub T minus 1. K sub T is the stress concentration factor as static conditions. Stress concentration factor. So we know from the tables before how to obtain K sub T. So if we find Q, we can solve for K sub F, and therefore we would expect that if Q is equal to 0, not sensitive, meaning that the plasticity redistributes all of the high stresses, then the fatigue stress concentration factor is nearly 1. It means that there's no amplification of the applied stress. For Q equals 1, very highly sensitive, then we can, or if we want to be conservative, then we use the fatigue stress concentration factor to be equal to the static stress concentration factor that we got from the earlier results. So if we solve the previous equation for the fatigue stress concentration